Okay, this week we are going to introduce a new, actually a new type of task, not just a new algorithm, which is quite different from what we learned previously with linear regression and classification. So it's called unsupervised learning because you don't have a clear goal where you are headed. So it could be classified that way, or it could be classified the other way. So the difference between supervised learning and unsupervised learning is one has a label, has a target. You know you want to classify the people as a high risk of obesity or not, or you want to classify them with heart attack, possibly heart attack or not. But here in unsupervised learning, you don't have this target. You could target them as their tall people and short people, or you could classify them as possibly obesity or not. So the main difference is between these two types of tasks is whether having label or not. So usually you group this all these cases according to their similarity with each other. There are two types of unsupervised learning. The one is most common is clustering. So you group the people, group the similar people, group the similar objects together. That's called clustering. And another type of task is association. You want to see which product are associated with each other. For them, someone buy bread. Okay, will they buy cheese or not? So that's called. So you want to find the relationship between these two variables. That's called association. Okay, these are the two main tasks under unsupervised learning. Clustering. So there are a couple questions we want to ask. How can we group them? The basic task is to group the cases together according to their similarity. But there are a lot of questions we can ask. There are a lot of possibilities here. It's not how you group them with males, females. That could be one possibility. And it could be how you group them according to their favorite sport. Or some people like sports, or some people don't like sports in this picture, right? Or you could group them with people or not. See, there's one special case here. So usually you want to ask what subpopulations, what kind of groups are there, and what are the sizes of these groups, and what they have common. Why do we group them? So after you build the algorithm, ultimately you need to answer, hey, how you grouped them together. What is the reason behind this algorithm? And then you want to check whether these subpopulations, whether these groups are cohesive or not. I mean, which means whether your model is good or not. And also you want to ask, can they further be split up? And are there any outliers? Okay, there are different types of clustering algorithms. The first one is the most commonly used, called central-based clustering. So typically, of course, this is not a good picture actually. At the beginning, here, okay. At the beginning, it doesn't have any color or shape. They are just random dots here, and then you want to cluster them. So what this central based means you pick up two centroid. This could be a centroid. And then you could pick up two centroid, okay? Supposing two centroid. And then you assign these dots according to their distance to the center. So if they are close to the center, okay, they are assigned to this one. And if are closer to the center, then they are assigned as a yellow or green. Yellow groups. They are close to this one, they are assigned to purple groups. So that's how this algorithm works. They're based on the distance to the centroid. We are going to explain more about this in a minute. And the next one is density-based clustering, which means based on like how you are close to other people. There are slight differences. So the other one, this one is also based on how you are close to the centroid. Here, it's not based on a centroid, but it's based on whether you have lots of neighbors or not. If you have lots of neighbors, you think, hey, you are in the in the popular area, in an urban area, okay, you belong to this community. But like these one only has maybe one neighbor or no neighbor at all. Then these are considered as the borders of this cluster, right? These has like two neighbors, okay, they are still in this area. And so it's based on its condensity of these dots. So like these dots, okay, within this distance, within this distance, it has no neighbor at all. So these are considered to be the borders of this cluster. And those with high density, then they are considered in the middle of this community of these groups. So that's the foundation of this algorithm. Okay. And the distribution-based clustering assume data is composed of distributions. So basically, it also uses a probability. If you are in this circle, okay, the probability you belong to this circle is high. And if you are like far distance from the circle, then the probability you belong to this red group is low. So but since your probability belong to this group is higher than this group, so you're still classified as red. So that's quite similar to the central based. And the hierarchical clustering means that you create clusters that has different levels. Like you could cluster them as animal and then different animal types. So what you have to answer is how many levels are there in these clusters, and under each subgroup, what are the other groups under this subgroup. If you see there's a clear hierarchical structure, then you should use this cluster. Okay, next we will detailedly explain the central based clustering. Okay, the most popular algorithm under this category is a K-means clustering algorithm. So how does that work? That said, first you will pick up two centroids randomly. pick up a 2 centroid randomly. For example, you could pick up a 3, okay? Or let's try 3. And here I pick up this one. And I pick up this one here. And I pick up a third one, maybe here. And then you assign each dot to the centroid according to their distance. So for here, let's try another dot, the third one at another position. At this position. This one will belong to this one, right? And these two will belong to this group. And these two will belong to this group. Yeah, this one is for them. And these two, all these obviously it's closer to this one. So it will belong to this group. They all belong to this group. Okay. And then the next thing the algorithm do is to, after you choose these groups, and then you reposition the centroid. So here, this after grouping these two dots together, the central for these two dots is still here, right? And these two, the centroid is still here. But for these ones, the centroid will be changed. As you see, this is not the centroid for these dots. It's probably about here. So this will be the new centroid. Okay. And then after this change, if you find the new centroid, after you find the new centroid, then you will reduce the step, just repeat the step we did to assign these all the circles to the centroid, to the new centroid. So these still will be here. These still will be here, and these still belong to this group. So you reassign the center, the points to the new centroid until it doesn't change. So here, will it change anymore? These are assigned to here, right? This new centroid. They all belong to this cluster, and these belong to this cluster. So it looks like they're not going to change anymore. We find the best. We find the best cluster for this choice. Do you think we find the best clusters for these dots? Are these the best center? This one group, this group, and then these as one group. Do you think this is the best clustering result for this data? I don't think so, right? Obviously, these should be in the same group, and these should be in the same. That will be a better result, right? So how we evaluate this result? Why do we say, hey, the result I just got, this one, it's not that good, and the result we observe, hey, these are as a cluster and these cluster, these as a cluster, it's better. How do we evaluate? Why do we say the second one is better and this one, this result is not good?
No, it splits the data, like the number of things in each bin is
Yeah.
the same, or would be the same with the other split than this split. Like this one has two that have 2, and one that has 8 dots. So if you had them split up so that each one had 4 dots, wouldn't that be a way of telling?
Do you mean like you want to split the dots evenly? Well, that could be. Actually, you evaluate this based on the variance. So for example, I can try. So you actually calculated the total variation of these centroid. For example, if we classified this way, this is the third one, the first one we got, right? And then the distance will be this one at this one, these add together, and then these dots to the centroid. So you add all the variations together, and obviously, this method. Actually, this method, okay, these 4 dots together and these 4 dots together. And if you classify that way, the variation will be smaller than this one. Obviously, these variations are very, very huge because they are far away from the centroid. So that's how you evaluate whether the cluster is good or not. But actually, so that's the first explanation of this algorithm. Actually, so the result, obviously, as you see, it's not that good. A lot of these dots, they are far away from their centroid. This result is actually not good. But that's the first explanation of this algorithm. They said, okay, you randomly pick up three centroid and then assign these until the centroid doesn't change anymore. However, as you see the result, it doesn't give me a good result. And I tried it in the code with the algorithm, the package gave me, it always give me a good result. I expect that is these 4 dots together with 4 dots together. So after research this algorithm, I found this explanation is actually wrong. The algorithm doesn't completely randomly pick up these centroid. What it does is, for the first one, it randomly pick up. Okay, I delete this. Yeah, okay. Another explanation is the first one, it randomly pick up. For example, I pick up this one. I pick up this one. And then the second one, it's not random. It picks up the furthest dots, the furthest data points from this one. So the second centroid will be this one. And if you want to, if you select k equals 3, you want to pick up the third one, right? The third one will be the dots that gives you the shortest distance to both dots. So for example, this one, the distance will be, actually it's not, it should be the shortest distance to both dots. But it doesn't work on this line. It doesn't work on, for example, if I have the MapleBot, I randomly pick up this one, and then the second one is the longest distance, then it should be maybe this one. And then the third one is the shortest distance to both dots. to both dots together, its distance to both dots together should add it up to be the smallest. So likely it will be like this one. Likely it will be this one that has the shortest distance to both. But it doesn't work on this line. Can we work on this line? Because they are all the same distance, right? The distance added together is all the same, right? So I cannot pick up the third point, right? But yeah, on like this 2D map works, we can see this one is the distance added together is the smallest. But on this like a 1D shape, it doesn't work well. This one is the middle. It's kind of the middle point between these two, okay? You can think of this as the middle point between these two. So we would choose either this one or this one, right? I choose this one as the third centroid. So now we do the classification. Okay, so these are close to this one. These are all close to this one. These are all close. And these, they are all close to this one. Yes, right. And these, they are all close to this one. And then after you find the clusters, you reassign the centroid. So the centroid will become here, change it to here. And these four, the centroid will be changed to here. And these four, the centroid will be changed to about here, right? And then you reassign these dots again until the centroid doesn't change anymore. So I don't think the centroid will change anymore. So as you see, this explanation, this method approach is much faster than completely random picking up of the three centroid. So what I believe is that this explanation is correct for the algorithm. What do y'all think? See, only with one pickup, only with one or two round, it's already find the centroid, and the centroid doesn't change anymore. But if you are completely randomly picking up the centroid, for example, I pick up these three centroid or these three centroid, then need a couple of repeats to find the best centroid. And as we did for the first attempt, it even gave us the wrong result. Right? But in this way, it guarantees the result is the optimum. So that's the two explanations of this algorithm. I think the most if you look up online, most of the articles, most of the videos will tell you the first method instead. But I tried and I tried a couple times. So and with this example, as you see, it gave me the wrong result. It could give me the wrong result. So I had to do more research and find this is a better explanation. The second one is a better explanation. So they're not completely randomly picked up, but the second one, third one, they are picked up according to their distance to the first centroid, second centroid. Okay. So what you do to evaluate this method is the variation within the clusters. You want the variation within the clusters is the smallest. If you classify this way, as you see, the variation of these are small, but the variation of these, they are huge. And these would be a better method because their variation within the cluster is smaller than this one. This one, it will give you a big. This one will give you big variation within the group. Right? See, these added together obviously is bigger than these. All these added together. So that's how we evaluate the clustering. In another word, we want these groups. Within each group, we want these cases are similar to each other. They're close to each other. And that's actually also how we find the best K. So this, as we said, the K, you don't know how many classes are there. You could have clustering them into 3 groups, or you could have clustering them into 3 groups. You could have clustering them into 5 groups or 6 groups. And how we find the best K. And how we find the best case. Think about this. So we want all the people, the data points in each group are closer to each other. The variation is small. One of those within the same cluster, the variation is small. If the K goes up, the variation, the average variation will increase or decrease. Decrease. More cluster. Yeah, so they're more similar to each other. And if we imagine if the K goes to, like you have n cases, and then you clustering them into n clusters. Okay, each cluster, the variation is 0, right? So the K is larger, of course, the variation is smaller. However, the reduction, it goes up, and at some point, the K doesn't go down that sharply. Here, from 1 to 2, 2 to 3, see, this K will go down very sharply. It will, the variation will go down very sharply. But at some point, at this able point, after this able point, the variation reduces very slow until it doesn't reduce anymore. So that's what we call the able point. Able point of the result. Okay, and that we say that is what we consider the best K. Okay. Next class we will use the code to demonstrate it. So today we just explain the algorithm, how it works, and then then we will use the remaining of the time for the project to see any question you have about project 2, we can answer. Okay. What to expect, there will be more attendance, better attendance at next class. I guess a lot of you are still working on the project today. Okay, so I think we'll stop here today, and then we'll continue this at the next class. Okay.